thing. Oh yeah, it is a very nice window. So yeah, let's. Here. Wait, give me a sec. All right, yeah, never mind. We're good. Okay. Yeah, share. All right, let me format this. Present and chat. There we are. Okay, welcome to day 3. Today we're talking about simultaneous games. So let's get started. So, quick reminder, what is a simultaneous game? A simultaneous game is a game in which players choose their strategies at the same time. Basically, the main feature about a simultaneous game, remember, yes, last class, sequential games, you have to follow one after the other. In the simultaneous game, it's all sporadic, right? You can't, there aren't multiple levels, it just all happens at once, and decisions are made. So let's quickly look at this game table real quick. So what you represent simultaneous games in the form of game tables. So yeah, like rock, paper, scissors, exactly. So in this case, we have a 3x3 game table. That simply means, 3 on the top. Wait, let me turn on my nice laser pointer. 3 on the top and 3 on the bottom. So player B has 3 options. They can go left, middle, or right. And player A has also 3 options. They can go top, center, or bottom. So yeah. So how do you read a game table? So suppose player A chooses top, and then player B will choose middle. Then the intersection is what occurs, right? It's pretty simple. If player A chooses top, player B chooses middle, player A is going to get 1 payoff, 1 point of payoff, and player B is going to get no points of payoff. So everybody understand that? I'm saying yeses. Anybody say no? I'm going to assume not, so let's move on. Okay, so Nash equilibrium. This is a bit of a kind of hard topic to understand a bit, so I'm going to go through this slowly and repeat myself a lot. So Nash equilibrium, the nice Wikipedia definition is a stable state of a system involving the interaction of different participants in which no participants can gain a unilateral change of strategy if the strategies of the other remain unchanged. That's a very wordy and kind of hard to understand definition. So a nice way of saying it is neither player would rather switch their strategy to a different strategy as long as the other player is going to stay the same strategy. So I'm going to explain, like, picture what it is, and then I'll explain why it's important, okay? So, click. So in this game table, which is the same as the previous one, this is the, Nash equilibrium, right? So let's quickly look at why this is the Nash equilibrium. So let's first look at rock, paper, scissors is a bit stranger just because there's a bunch of different payoffs, but let's talk about this. So player A, so suppose player B is going to stay with left, right? They choose left no matter what. Then, so player A, if they choose top, they get a payoff of 1, right? But what if they decide to change? Suppose they say, no, I'm actually going to choose center. Then they get a payoff of 0.9, which is less than 1. And if they go with bottom, then they get a payoff of 0.8, again, less than 1. So as long as player A knows player B is going to choose left, they're going to have to stay at top. And the same thing is valid for player B, just, the other way around. So if player A is going to stay with top, then if player B switches from left to middle, they're going to switch from 1 payoff to 0 payoff. And if they switch from left to right, then they'll change from 1 to 0. So as you can see, as long as both players, as one player stays where they are and the other player changes, then they're actually worse off. So you might be wondering, well, this doesn't sound super important. Why do we care? And why is this the right answer? Well, remember, we are assuming all players are rational, and thus they have to have this theory of mind that they assume that the other player is going to make similar decisions. Yeah, player A can anticipate player B's moves because they understand what they're thinking. They're thinking, okay, they're going to have the same process as me because we're both rational. So we should both go for the Nash equilibrium because I know that if I stay with the Nash equilibrium and if they switch, then they're going to be worse off. And if they stay with their option for the Nash equilibrium and I switch, then I'm going to be worse off. So in that case, it's not the optimal solution, but it's the solution in which case both players kind of have a mutual understanding. Pick rock and rock, paper, scissors. The problem with that, again, rock, paper, scissors isn't a great game to discuss Nash equilibrium with, because it's, somebody wins, somebody loses, but so this is a kind of abstract game with random payoffs and stuff, but with rock, paper, scissors, it's very defined, and that's not exactly good because, again, there's some payoffs in which some people get nothing, and there's some payoffs in which one person gets 1 and some person gets 0. But the fact that somebody, there's like 3 separate things, well, actually 6 separate, right? Well, somebody wins and somebody loses, or they all tie. That's, you can't really describe a Nash equilibrium with that, because there's so many options, and it's, in the end, you're combating each other. So let's quickly go over why this isn't the Nash equilibrium. Just to quickly make sure that everybody understands, can people describe why this is not the Nash equilibrium? Kind of, but not exactly. When I say, again, not quite, so I'm going to address both of these. So because you can change your strategy at any time, that's not exactly what we mean when we say this. We're assuming that it's not changing your strategy. It's just doing something else, I guess. Remember, it's all simultaneous. You can't change your strategy. It's just like in a hypothetical mini game in someone's head before the game occurs, then, that's what they think about, so they'll move. That's just pure luck, I guess. I don't know. Again, rock, paper, scissors isn't exactly a great topic for Nash equilibrium. Not the biggest payout for who? Because, you're on the right track, but we need to get a bit more specific than that. Yes, exactly, because player B would benefit from changing their strategy. So, yeah, exactly. Player B, they could switch to left and do something better, meaning that it's necessarily not the Nash equilibrium. So yeah, that's exactly what it is. But the reason it's not the biggest payout is because, is it unpredictable? No. Remember, all players are rational, and we can have this theory of mind that the other player is also going to go for Nash equilibrium. So if you can ever define a game, in some sense, it's like unpredictable in a way. Like, how do I phrase this? Turn the sync. So it's, in rock, paper, scissors is unpredictable, right? Because each of the 3 options, in essence, nothing is better than the other, right? But in this game, because there is a Nash equilibrium, both players, if they are rational, have to go to that. That is the thing. It's not necessarily the optimum thing, as I'll, in this case, so it's 1-0, right? But, okay, this isn't a very good case. This is, okay, let's go way back. This is an example of a constant sum game, right? Actually, no, it's not. Yeah. Sorry. In this case, this is the best one because this is, never mind what I said. This is not constant sum. That was completely wrong. I forgot my own slides. But yeah, it's, when we're talking about simultaneous games, this is kind of a weird thing to think of. Players are making their decisions, at some points, but there's this assumed time before they make their decisions at the same time, when they're just thinking about what the other player is going to do. And that's the period in which they choose their decision and can kind of visualize what players are going to do. Yeah, exactly. Yeah, I messed up a bit. That's my bad. So how do we find this? This kind of seems, a bit conceptual. Is there an easy way to find this? And well, we're going to talk about it. Yeah. And I forgot this slide existed, but yeah, middle would rather be 1 than 0, so this isn't Nash equilibrium. So one of the ways we can find what the Nash equilibrium is using dominant strategies. So a dominant strategy is a strategy that, no matter what the other player chooses, will always yield the highest payoffs for the player using the dominant strategy. If a player has a dominant strategy, then the other player knows that the first player will always choose their dominant strategy. Basically, it's the best one. This is the one you always go for, because it always beats out the other strategies. So let's go on to this slide. I'm going to kind of hide the chat so I won't be able to perfectly see you guys for a bit. So we're going to be using different game, unless I specify otherwise, we're using different game tables. So keep that in mind. So in this case, we have a new game, right? Player A can choose top, center, bottom, same choices. Player B can choose left, middle, right, same choices. But now there's a totally different payoffs, right? If player A chooses top and player B chooses left, then player A gets a payoff of 10, while player B gets a payoff of 7. Yes, exactly. That's why we have to assume all players are rational, so that we can make set assumptions. That's the point of rationality, really. It's so that we can assume that people have theory of mind and can understand what people are doing. So I'm going to quickly read over the game table. Player A goes top, player B goes left, 10-7. Player A goes top, player B goes middle, 11-5. Player B goes right, player A goes top, 9-4, et cetera, et cetera. Yeah. So let's look at, suppose player A is going to do a little thought experiment. Suppose he magically knows that player B is going to go left. Which option should player A go for? Exactly, yeah, top, yeah. Everybody's getting that. Player A is going to go top in this case. Okay, so everybody understand why? Just payoffs, 10 versus 2 versus 1. No spoilers. Player B. So now suppose player B goes middle. What should player A do in this case? Yeah, exactly. Yeah, still top. Yeah, again, no spoilers. I'm trying to, admittedly, this is a little bit of padding, but you know what, yeah. If player B goes right, player A is going to go top. So you've all noticed that player A always chooses top. So that means that top is the best case, and thus, if we refer back to our definition, it's always a dominant strategy. I assume everybody understands why it's a dominant strategy, or should I go back to that slide? No one's saying anything, so. Why is it an I guess? I don't know. Is there a problem? Oh yeah, okay. I don't know, but yeah. All right, so clearly player A is never going to choose center or bottom. So now let's kind of step into the shoes of player B. So player B has run the exact same thought experiment and notices that player A, no matter what they choose, is going to go top. So they can just completely just negate those two. They're just gone. Pretend they don't exist. Because player A is always going to choose top, right? So now player B themselves has a choice. They can either go, like, in this case, player A, it's no longer a game, really, once you eliminate center and bottom. Player B now just has to make a decision because player A is going to choose the same thing no matter what. So what's player B going to go for? Yeah, left, exactly. Player B is going to go left, and thus that's the Nash equilibrium. So let's just quickly go back, and let's make sure that that's the Nash equilibrium, right? So assuming player B stays left, if player A changes from top to center, they go from 10 to 2. If player A changes from top to bottom, they go from 10 to 1. So obviously, they're not going to change. If player A stays top, if player B changes from left to middle, they change from 7 to 5. And if they change from left to right, they go from 7 to 4. So clearly, player B doesn't want to change if player A stays the same, and player A doesn't change if player B stays the same. So this is pretty obviously the Nash equilibrium. But what if you don't have dominant strategies, right? Well, then our second technique that we're going to use, or not technique, a second definition that's going to be used for a technique we're going to use is dominated strategies. So a dominated strategy is a strategy that no matter what the other player chooses, will always yield a lower payoff than another strategy for the player using the dominated strategy. If a player has a dominated strategy, the other player knows that the first player will just never touch it, right? So I'm just going to, a misconception some people have is that the dominated strategy is the worst strategy. And while that's is dominated by a different strategy, and while that might be true, dominated strategies just have to be the worst, right? But it doesn't have to be worst when compared with only one thing. No. The reason it's the worst is because it just is never picked, right? It doesn't have to be the worst in specific scenarios, but overall it has to be the worst, right? So suppose it does actually really close all the time to the next thing, but it just never gets picked, right? So suppose like a bunch of different strategies in different scenarios all have 10, but in every single scenario, our dominated strategy is 9. So while overall it has the best, it doesn't, it's actually dominated because it doesn't get picked, right? So let's look at this. Again, another game table. So I'm just going to read off parts of it. Pointer, pointer. So player A goes top and player B goes left. You get the point. I'm just going to leave the slide alone for like a minute or so. So yeah, I'm just going to leave it. So everyone good? Has everybody read enough of the game table to get a general idea? I mean, we're going to obviously go for it. Wouldn't the center be a dominant strategy? I'm going to show you that you're wrong. I don't want to be mean, but that's we'll show you that it's not. So I'm just going to start. So if player B is necessarily going left, right? So again, we're in player A's head. Player B is going, suppose player A, magically knows that player B is going to go left. Then player A is going to go with which one? Yeah, center, exactly. Everybody's right. I forgot that I did all of them at the same time. So if player B goes middle, I'm just going to spoil it. Player B goes middle, then they're going to player A is going to choose center, and if player B goes right, this is the reason why center is not dominant. Player A is going to go top, right? Because 7 versus 4. Do you understand? Whoever asked that, Zaire, do you understand now? Yeah. Okay. Cool. So yeah, it's pretty obvious. But as you can see, player A never chooses bottom, right? And in this case, player bottom is just absolute the worst. But in some other examples, who chooses first? Again, this is whenever we talk about it like this, we're assuming it's like a thought experiment in either player's mind, and both players are thinking about this at the same time, simultaneous game. You good? Okay. So obviously, as you can see, player A is never going to choose bottom, right? It's always worse. So it's just gone, right? Gonzo. But you might be thinking, well, we're not done, right? There's still 6 options. So now we do the same thing, but with player B, right? So if player A chooses top, player B is going to go and choose something, right? So we apply the same idea. So, 6 versus 4 versus 0, they're obviously going to go left. 6 versus 7 versus 1, they're obviously going to go this one. And, right is dominated, right? The player B is never going to choose right. They're going to, in this case, they choose left. Excuse me. In this place, they choose middle, never right. So right gets eliminated. And now we have a much simpler 2x2 game. So then we go back to player A, and we can see that, so now we have this smaller game table. If player B goes left, then player A is going to choose, center. And if player B chooses middle, he's again going to go center. Getting more points. Remember, it's not about it's not about difference in points. It's just how many points you get, right? You good? I am going to assume you're good. It's just point values, right? In this case, it's 7 versus 6. If we want to do it in terms of winning versus losing, then we usually, like the person who wins gets 1 and the person who loses gets 0. Or if it's not how much you win by, it's just how many points you get. It's again, payoff. We don't care. You only care about yourself, right? So we can ignore the 6. He only cares about the 7. He only cares about the 8. It doesn't, well, the other person doesn't matter. You just want yours, right? You only care about yourself. But again, let me return back to this. So player A is going to now that we have this reduced game table, player A has a dominant strategy of going center. So top is eliminated. And now you kind of, it's not no player B, it's you assume that there's a player B, but player B scores their score. You don't care about their score. You want what's best for yourself. It's not you versus player B. It's you and player B making decisions. That's a good way of thinking about it, because yeah, I mean, or if you're player B, you don't care about player A, right? It goes both ways. But as we can see, we've eliminated to a 1x2, so it's no longer a game. Now it's a decision. Player B is going to go with center, right? Everybody understand this? Everybody cool with this? In this case, it's not like chess and stuff. Chess and stuff, if you're making it into a large sequential game, then the payoffs, it's either one person gets 1 from winning in the end, and the loser gets 0, or they both get 0 from tying. That's it, right? It's not complicated payoffs. But does everybody understand this? Yeah. Yeah, stalemate. Both players get 0. So let's quickly go back to the very first slide. And let's quickly confirm that this is the Nash equilibrium, right? So suppose player B, again, we're doing a little thought experiment. Player B is going to have to choose middle. So now player A can choose between top, center, or bottom. If they choose top, then they get 3. If they choose bottom, they get 2. If they stick with center, then they get 8. It's the best for them. Now we do the same thing about player B. If player A stays center, if player B changes from middle to left, it's 7 to 6, and if they change from middle to right, it's 7 to 1. So clearly, this is in fact the Nash equilibrium. So what if there aren't dominant and dominated strategies? There are going to be, but what if there aren't enough to complete something, right? What if it gets more complex? What if you have a large thing? And what if you just don't have the time to do all of this? This was a pretty lengthy process, right? Even with just a 3x3 table, we had to do several steps. So this is the best way of doing it. And if you're given a game table, this is the way you should be doing it. It's called best case analysis. So in every given scenario, what should a player choose? And it's just the overlap and best options is the Nash equilibrium. And that's a bit of weird wording, but it's a lot easier to show than to explain. So here's our new game table. Again, different. So just inspect it for a bit. I'll, wait a minute. Oh, does everybody understand dominated strategies? Are we good on all that before we move on? Okay, so does everybody also, again, next question, everybody get this? Most of the time I have to make our own game tables. I mean, if you're taking, that's kind of a weird question because it just depends on the scenario. If you're in a real game theory class, then for homework, they're going to assign a lot of game tables. Trust me, that's going to be, well, you're going to have to deal with a lot of game tables. But if you're doing your own little project, then you have to assign, point values, right? And yeah, again, if you're in just a class, yeah, top would be best case for a player, right? I don't remember, but I don't think so. So everybody's read this, so let's quickly go through it. It's pretty simple, in every given scenario, what do they do? Player A chooses, if player B chooses left, player A is going to go center. If player B chooses middle, player A is going to go top. If player B chooses right, then player A goes top. And 12 versus 7. That's why the top isn't necessarily the best. Now, you might be thinking, okay, let's just do a dominated strategy, right? We don't have to. Now we just do the exact same thing, but we flip it, right? So now we assume that suppose player A is necessarily going to go top, player B will go with middle. If player A necessarily goes with center, player B is going to go middle. And if player A goes bottom, player B is necessarily going to choose bottom. So the overlap over here is 8-8, and that is the Nash equilibrium. And that was just so much faster, right? And this is the way you're going to do it. No, it is simultaneous. Every time we do something like that, we're just doing a little thought experiment where we say, okay, assume this, assume that, right? Assume that player B has to choose left. Assume that player B is going to choose middle. Assume player B is, yeah. So again, this is just the easiest way to do it. It's fast, and it just does a bunch of circle stuff, you know. And it's kind of a mix between dominant and dominated strategies, but you don't have to alternate between players. It's just instantaneous. And this is, if there, no, not necessarily. Basically straightforward rock, paper, scissors. Almost. I see where you're coming from, but not quite. What if there is no dominant, then it's luck, right? No. Again, as long as there's a Nash equilibrium, players should gravitate towards that. Because so both players are having this exact same thought process because we're all assuming all players are rational. If the other player does go Nash equilibrium and I don't, then I'm going to be worse off, right? That's the definition of Nash equilibrium. So because of that, if the other player goes Nash equilibrium, then I'm going to go Nash equilibrium. And because they're having the same thought process, they're thinking the same thing and will also go Nash equilibrium. It's kind of a weird theory of mind thing, but again, that's the nice thing of dealing with rational players. Everybody is, doing the correct thing. Would rock, paper, scissors be a game without Nash equilibrium? So, yes. Rock, I think, I would have to do it, and I don't have any pencil and paper with me, but I think so. Let me, you know what, no, it's not worth it. I'm pretty sure it is, yeah. Remember, if they know your dominant strategy, they can't use it against you, right? Because they know that if you have a dominant strategy, that if they choose anything else other than what leads to the Nash equilibrium, they're going to be worse off, right? Players don't care about the other players' payoffs. They only care about themselves. I don't care about how you're doing. I just care about how I'm doing. So if I know that you have a dominant strategy, I know that if I don't pick the thing that's going to lead to the Nash equilibrium, I'm just going to be worse off. Exactly. If somebody has a dominant strategy, always choose that. That is the go-to. That is the best. Yeah, exactly. So any questions about this? I see one no, which is good. In this case, player A is better off, right? I mean, no, not really, because better off. Again, the thing about game theory is that you kind of don't players players don't really care about the other person's payoff, and in this case, remember they both get 8, so they're actually the same in this case, right? So yeah, the Nash equilibrium is kind of a weird concept because it's not the optimum, right? It's this weird idea, in some cases there are just scenarios in which case both players can do better in case of a Nash equilibrium if you don't use a Nash equilibrium, and that's actually a pretty interesting thing, and we're going to talk about that. That's like our last slide, a specific game, but it's just it's a weird concept. It's like what would they agree upon? Exactly, that's the best way of thinking about it. If both players are kind of cooperating and kind of not cooperating at the same time, it's this weird twilight zone, I guess, of cooperation. So yeah, both players just want what's best for themselves, and they know that if the other player is thinking rationally, then if they don't also think rationally, then they're going to be, get a worse score than they could have gotten. So yeah. So far we've looked at games with one Nash equilibrium, but is that the only number? Can there be more than one? Can there be less than one? And the answer to both is yes. Not only can there be more than one equilibrium, which is, kind of interesting, but not super interesting, there might not be just a simple Nash equilibrium. And that is the interesting one. That is interesting, and that's for next class on Tuesday. So everybody just quickly read this, and I want you guys to figure out what the two Nash equilibria are. I want to make sure everybody gets it. This might take a bit, and there are two of them, just a heads up. So try to figure out what they are. We'll get that. We'll get to there. Don't worry. We're getting there, and that's cool. And we're going to do that. That's all we're going to be doing tomorrow. Not tomorrow. Tuesday. You know what I mean by tomorrow. Next class. So just quickly calculate this, and if I don't get anything, then yeah, I'll demonstrate. But I want to make sure everybody understands this, because it's not the easiest thing in the world, but just practice. If you want to get good at finding Nash equilibria, just search up game table, practice. You'll find tons of stuff. It's really, it's one of those things that comes with practice, yeah. We're doing Prisoner's Dilemma? Yeah. No spoilers, but that's the very last thing. And yeah. So good on you for knowing that. We're talking about simultaneous games. Shoot. How do I do this? So simultaneous game. Do you remember what a simultaneous game is? Yeah, we talked about Nash equilibrium, but do you remember what? Yeah. Okay. Cool. So Nash equilibrium is just. I'm just going to go back to the definition slide. Just read that. Okay. Let me check. Yeah, this is just the definition. Sorry that you're late, but okay. We were on the fun slide. Okay, here. So 4, 6. That's what you're saying one of them is. And what's the other one? Also, yeah, 7, 10 is one of them. And just a heads up, 4, 6 is incorrect. You might want to redo it. Again, this is not easy. If you guys want, I'll do it over again. Oh, shoot, I did that. Well, now you saw it, but try to do it yourself. I'll just wait I'll wait 30 seconds. Slightly more than 30 seconds, I don't know. Just to see if anybody, because 710 is correct, but there's another one. Again, that's one of them. Yeah, okay, we're good. 710 and 5-4. Yeah, exactly, we're good. Good job. Exactly. So in this case, there are actually 2 Nash equilibria, right? You guys seem to get it, so I'm not going to do it over again. But both, if top middle resulting in 5-4 and center left resulting in 7-10 are Nash equilibria, which is pretty interesting. And in this case, because one of them is clearly better, they're probably going to gravitate towards the 7-10. If both players are thinking rationally, they're saying, okay, they're probably going to go for the thing that's better than them. I'll probably go for that. Technically, you can't assume that per se, because both are Nash equilibria. But if you kind of take kind of a little bit of a less theoretical, like ever so slightly less just thinking about math approach, you're like, yeah, obviously. Why would I go for the other thing, right? So yeah. Everybody cool on that? So in this case, one Nash equilibria is clearly better for both players, but there is an example in which there's 2 Nash equilibria, but one's better for one other person, and we'll get to that. So next one. What if there's no Nash equilibria? I'm not going to make you, we'll get there. We'll get there. Stop asking for Prisoner's Dilemma. That's the last thing, and it's one of the cooler things. So can everybody just make sure that they're, yeah, we'll get there. We'll get there. It's cool. But can everybody just confirm that there is no Nash equilibria here? Just quickly say that you understand that there isn't. If you don't, then I'll show you that there isn't. I have 1 year. which is the correct way of saying yeah if you're too lazy to do the full yeah. Okay, explain please. I'm getting one explain. Okay, so I'm gonna try to do this cool thing with more. How do I do? Never mind. You can see my laser pointer thing, right? Yep. I didn't mean to. I mean, so let's just this is the thing. So again, we use best case analysis. So if and remember, blue represents player B and red represents player A. I don't think I said that, but it was kind of implied. So suppose player B chooses left. Player A is going to choose center. If player B chooses middle, player A is going to go top. And if player B goes right, player A is again going to go top. Reverse for player B. If player A goes top, player A goes left. If player A goes center, player B goes middle. And if player A goes bottom, player B goes right. So as you can see, there is no overlap, right? So there isn't a Nash equilibrium. Does everybody understand that? Why there's no Nash? Because I'm going to get a bit more weird with this, because no Nash, again, that's pretty cool. I see one yeah. So I'm just hoping for a few more yes if everybody understands why there's no. I see one more yeah. I see, yeah, great, okay, cool. All right, so the interesting thing about this is that now the players can't really reach an agreement per se. So what are they going to do, to maximize their payoffs? Because no matter what, you can no longer make that nice rational assumption. This guy's going to go for that. Well, now you have to, this is, again, that's all we're going to be talking about Tuesday. It's called the mixed Nash equilibrium. And basically, now both players have to be like, okay, remember, there is no dominant strategy here. All three of the methods will find Nash equilibrium the same way. All three of them work. Dominant strategy, if there is none, then you can't, there is no dominant strategy, right? Player A goes both top and center, and player B goes with all three. So there is no dominant strategy in this case for either player. Are you good? Does that make sense? While, yeah, player A does have a dominated strategy, but again, that only makes it, even if you, I don't really, pretend that bottom doesn't exist, then there's still no Nash, right? Because then in that case, it doesn't matter. Maybe I didn't make this clear. All three of the methods, dominant strategies, dominated strategies, and best case analysis, will all find the Nash equilibrium all the time. Like okay, I said that wrong. All three of them can find Nash equilibrium, and if all three of them work, then they'll all find the same Nash equilibria. There's only, there's the Nash equilibria are set, right? If there is no Nash equilibria, then however you use, there is no Nash equilibria. And if there is some Nash equilibria, they'll all find the same Nash equilibria. So while there is, a dominated strategy here, it doesn't really matter because using best case analysis, we can determine that there is no Nash. So is everybody cool with that? It's, again, this is a bit of a weirder topic, but I mean, again, next time is going to be fun. That's when the math starts. I see another yeah. All right, people seem to be good. Give me a sec. Oh, sorry, I didn't mean to shoot. Okay, so in the case that there is no Nash equilibria, both players have to instead find out what the mixed Nash equilibria is. So basically, both players are thinking, okay, I can't, assume what my partner's player, whatever, is going to do. So now I have to choose each different strategy I have with a specific probability, right? Maybe player B chooses right with like X probability, with middle goes Y probability, and left with one minus X, like 1 minus in parentheses X plus Y. Do computer bots do that? I mean, if there is no Nash, then you have to do it. That is the correct thing to do. So not only do computers use it, if you're ever in a scenario in which there is no Nash, oh, do computers? I mean, if you have to remember that everybody uses game theory, not just computers. But I mean, um, the calculation, it's kind of hard to wrap your head around why it works. But once you do, it's not super hard. Uh, it's, I mean, computers use it, of course, but you're going to use it hopefully at some point. I've not really had the opportunity to use game theory in real life, but I assure you, when I do, I'm going to make a big deal out of it for anyone who pays attention, whoever cares. So yeah, and again, all this we're covering this Tuesday. That's math day, like numbers, and this has all been circles, shapes, fun, but that's like actual math. So that's why there's that prerequisite. So yeah. So there are a handful of two-player games that you just should know about, right? These are the 5 big 2x2 games. Remember, this is 3x3, left, middle, right, top, center, bottom, 3x3. So these are all 2x2 games, and you should just know these, right? And here's the prisoner's dilemma for all of you who are asking. And these are all incredibly important because in a lot of scenarios, in real life, if it's complex, you can just figure it out, right? You can just kind of narrow it down and make it into one of these 2x2 games, and you can figure out what you're supposed to do. And if you have something like this, it's pretty easy to figure out what to do. So let's start off with pure coordination. So so now we're making this a little bit less abstract. So player A and player B, let's call them Alice and Bob, just because fun names. They've contacted each other and they're like, okay, let's play racket sport. But right when they hang up, they forgot to say what kind of racket sport, right? So now both of them have to decide which one they're going to play. They can either play tennis or badminton. Both has a choice, right? So if they both play tennis, they have fun. They both play tennis. If they both play badminton, they have fun. They play badminton. But if they choose different things, if player B goes to the badminton court or player A goes to the tennis court, you can't play badminton by yourself and you can't play tennis by yourself. And that's no fun, so neither of them get a payoff. So in this case, there's 2 Nash equilibria. Both play tennis or both play badminton, right? Can everybody understands the basics of this game real quick? And they have to choose between one of the 2. Yeah. So this is kind of an interesting thing to think about. Do you have any situations that you think could be simplified into pure coordination, where both of you just have to choose the same thing and you're good, right? And that's it. As long as you choose the same thing, it's fine. It doesn't matter which of the 2 separate things you choose. It's cool. This specific game can be generalized to, more than just 2x2. This can be like, done in the 3x3 game. Maybe there's an additional racket sport, tennis, badminton, and pickleball, I guess. That's the first one that comes to mind, and as long as they all pick the same thing. Same idea. So does anybody have, a real life example of this? Whether you've been in it or no? Come on, I know you guys have something. I gave a real life example. It's not that hard. If not, then I'll move on, but still. Still 15 minutes left. If that's an example, could you be more specific? And if it's not an example, just say it's not an example. I don't know. When you try to... Oh, okay, yeah. Yeah, exactly. The nice high five example, if you're content with not high fiving and high fiving at the same, you either high five or you don't high five. As long as nobody gets slapped, it's fine, right? Exactly. That's a pretty good example. Yeah. So one example is good enough because I doubt we're going to get any more. So assurance, I couldn't come up with a cool picture for this. So now player A and player B, same idea. They're like, okay, let's go do something, and so they hang up. And they forget to say what that something is, but both of them know they're either going to play tennis or go to the coffee shop. When 2 people are walking in opposite directions and you have to go around. Could you be more, I'm just going to go back to the previous slide then. Could you be more specific? I don't quite understand. to. Oh yeah. Exactly. It's kind of like reverse thing, right? It's instead of having to pick the same thing, they have to pick the two separate things. But yeah, you either both go left or right, and if you hit, that's bad. Um, and if they both choose the same, yeah, exactly. That's a good example. Yeah, they want to choose opposites. It's like reverse coordination. It's pure incoordination, shall we say? But let's return to assurance. So, you know, if I'm just going to skip the preamble. If both people choose tennis, they both get a nice large payoff of 10 because everybody loves tennis, right? But if they both go to the coffee shop, that's lame. Who wants to go get coffee when you could be playing tennis? So while they do have a small payoff, it's not as great. And if they choose opposite things, that's no fun. It's no fun. You can't play tennis by yourself. And I'm neutral towards swimming. It's fine. I don't care. But if one goes tennis while the other goes coffee shop, there's nothing, right? So, coffee bad. Exactly. Yes. So, as you can see, tennis is just the clear thing. Oh shoot, I did not mean to click the slide. So they're both they're both going to choose tennis, right? It's like our two Nash equilibria example from before. One is just clearly better, so they're going to choose that, right? And many examples of this at all. It's like, again, what are some real life examples? If everybody understands what this is, are there any real life examples people can think of? Come on. Yeah, like if two people are saying, okay, let's meet up, and we can either go swim or go on a run, right? And I'm assuming you just prefer swimming. Uh, I mean, running on a hot day isn't exactly fun, so for the sake of the argument, let's say that swimming is just so much better. Hypothetically, I'm not calling anybody out if you prefer running. So yeah, I don't know. I'm not saying anything. I'm not taking any sides. I'm not a great fan of swimming, and I'd rather go biking than running. Biking on a hot day, you're going fast enough, hopefully, that the wind and stuff. So yeah, if both go swimming, it's great. You get, you're not, you know, uh, getting super hot. You're in the water. It's nice and cool. But if you go running, you're having fun. You're talking to each other, but you're also running in, however hot it is, and it's not fun. But you're still, talking to each other. There's a minimal amount of fun. But if you don't do the same thing, then what's the point, right? What's the point of doing it by yourself? Okay. Aha. That's the exactly next thing. It's called okay. So it's called Battle of the Sexes. That's like its historical name. I'm not going to get into why. Um, but if you really want the story, just search it up. It's kind of weird. But yeah, so player A and player B, it's the racket thing example. Like, okay, hey, let's play rackets for it. Cool, hang up. And then they don't remember, right? So, but in this case, player B prefers badminton over tennis, and player A prefers tennis over badminton. Suddenly, while both of these are Nash equilibria, both have conflicting interests. And this is a pretty interesting game, right? This is like if somebody likes coffee and tennis, but the other one likes tennis over coffee. Now they can't decide, and now they have their interests aren't aligned, right? So this is the interesting part, because now, while there is a Nash equilibrium, it's really hard to think about, like, right? So, Battle of the Sexes, not really. It's not about women's rights. It's a bit. It's just like the husband wants to do something, and then the wife wants to do something else. It's this. Just search it up, I guess. I don't know. It's not super bad, but it's not super great either. So I'm going to refrain from talking about it. So is it? I don't know. Maybe it is. I thought it was about a husband and wife, but that's what I learned. Maybe that's the nice padded down version. But so you might be thinking, how do I solve this? Well, I anyway. So so in this case, they both have conflicting interests, and that's the problem. How do we choose what to do? And while there's Nash equilibria, suddenly you can't just rely on the Nash because there's two of them, and one isn't clearly better than the other. So it's hard. What do you do here? And you can't really do anything else, because even if you decide, suppose you do this multiple times, right? If you manage to work on the first time, then you're good, right? Then you say, okay, then let's do the plays I prefer the second time. But if you don't manage to do it on the first time, what then, right? Then it's then it's a bit confusing. So this is probably an easier example to come up with. So does anybody have any examples for this one? Are you umming at the reasoning of this? I assume you are. Yeah, okay. it's weird, but I don't know why they kept the name. In my opinion, it should be changed to something else, like tennis versus badminton. And everybody make that the official thing. When everybody gets their degree in game theory, try to push for that when you get your doctorate. But yeah, anybody have any real life examples? Because this is a pretty common occurrence. Come on, I know there's some examples. I have no idea what's going on in chat right now. Same with swimming and running. Yeah, suppose maybe it's not a hot day. Somebody prefers swimming. Somebody prefers running. Which one are you going to choose? And yeah, that's his idea. You stole it, coward. All right, so chicken. So this one is a bit more violent. So in the 19-somethings or others, I don't remember, 50s, I think. So there's this game called Chicken. So you're on a one-lane road, and there's two cars, and they're driving towards each other, and chicken is not fun. So basically, they're just who's chicken, right? Whoever swerves and decides not to get hit is this chicken, and whoever goes straight is considered the cool guy, brave and whatever. So whoever swerves, loses a bit of honor, so they get a payoff of -1. And whoever goes straight, they're the cool guy. So they get a little bit of honor, so it's 1. And if they both swerve, they're both lame, but nothing happens. But if both players decide to not swerve, suddenly, there's a car crash. That's bad, now the cars are wrecked. If they aren't dead, they're going to have to pay for hospital expensive. Yeah, but they still go in a car wreck. I don't think the honor matters if you're in a car crash, because you might be, dead. So we're assuming that if they swerve, they kind of do this thing where they completely veer off, so they're fine. So yeah, a lot of chicken jokes. Okay, I guess that's the thing. So give me a second. One moment. Literally 1 moment. So yeah. There are two Nash equilibria in this case. One person goes straight and one person swerves. But the problem is, who's going to lose their honor, right? It's pretty similar to the previous thing. They both would rather, doing the thing. But, if they can't decide, they're both probably going to go straight, and then they're going to crash, right? And that's bad. So somebody has to be the person to not crash and take a little bit of whatever to their honor. So it's kind of a weird, bad thing. And it's not exactly fun. So this one might be a bit hard to come up with an example with, because I hope none of you have played Chicken, because I don't know if a lot of you would be. I mean, if you're taking this class, you're not stupid enough to play this, like in real life. Although, yeah, the average. Exactly, yeah. It's not good. No. Yeah, it's flight or fight. Exactly, yeah. If you go 5 miles an hour on a beach, well then, yeah, but the crash isn't going to be as bad. You know, you might get damage to the car, but what's the worst that's going to happen? So, okay, I didn't realize we're actually running out of time, so I'm just going to move on to the cool thing. Prisoner's Dilemma. This is what some of you were asking for, and this is cool. And we're not really going to be able to talk about the cool part of this because that's hard, and we're not talking about it. Okay, so here, this one kind of has a long backstory, and because we're running out of time, I'm going to go through it super fast. So there's two suspects, and they're captured by the police, and they're put in separate rooms, right? So they can't communicate with each other. And the police say that, tell them this. So both of you are suspected, I don't know. Both of you, so the police, you know, the criminals can't talk to each other. They're in isolated cells. And to each prisoner, the police say this. So each prisoner has a choice. They can either just keep their mouths shut and not say anything bad about the other prisoner, or they can, you know, just backstab the other guy and say, no, he did the bad thing. He's the one who robbed the place. So if both prisoners stay silent, the police only have enough information to get them for loitering. So they only get 1 year in prison. Remember, negatives are bad, so they get 1 year. If they both rat the other person out, if both rat the other person out, then, you know, they both say, oh, the other guy did it. So then, you know, they both go into jail for a long time. But if one person rats the other person out while the other person stays silent, then the person who stays silent gets like massive 10 years when the other person goes completely free. So yeah, this seems counterintuitive. Like, that seems a bit weird. So the interesting part about all this is that, again, we're running out of time. The Nash equilibria is actually both rat each other out. And it might kind of seem weird. Why is it defect and cooperate? That's just the words that the official thing uses. Cooperate refers to cooperating with your partner, and defecting refers to defecting from your partner. I don't know what split or steal is, and I don't have enough time to ask. So again, this is the Nash equilibrium. And it's clear that if they both cooperate, it's better for both of them, right? That's the thing that's best. But because it's, you know, if they both choose to cooperate, if, you know, you think, oh, they might cooperate, then you instead defect, and suddenly the other person's just terribly off. So if you recall repeated games, this is the main thing that like people like to do repeated game studies on, right? If you repeat this over and over again, what's going to happen? So there's this entire like I don't think this is a thing anymore, but like there's this competition. There was in like the 80s, I think. So this guy, he said, okay, write a computer program that can, you know, based on previous information about like previous times you've interacted with the other program, you have to figure out what to do, right? So, and then these computer programs keeps on playing it, stop spoiling it, but that is the correct answer, yeah. So there were tons of different things submitted, but in the end, the one that did the best is called tit for tat. Good job, you knew the cool, funny word. But basically how that works is that, so at the very beginning, you cooperate, you're nice, and if they continue to cooperate, then, you know, you continue to cooperate. But if the other person suddenly defects on the next iteration, then you defect as well, right? You say, no, I'm not going to deal with that. If you defect, I'm going to defect too. So that's how it works. If you, again, this is one of the coolest things to look at. Once this course is done, I highly recommend you check this out. And we're already over time slightly. So, stop share. Give me a second. Nobody leave. What was the 24 people? I don't know. So, we're done here. So, yeah. You guys can leave now. This was the entire lesson. We're going to be talking about, if you recall, the thing with the no Nash equilibrium. And that's going to be cool, but it's going to be dealing with math. So maybe get pencil and paper. I don't know. Not really. I explain everything nicely. So yeah, bye. Everybody have a good time, I guess. And I'll see you Tuesday.